I invite our last speaker, Milan Klöver, who will present his project Elefridge.jl. Milan, the floor is yours.
Yeah, great. So this is my project, which I just like the work in progress title is Elefridge.jl. It's actually a project on climate data compression, and basically it's just this like underlying question of like how do we put an elephant, meaning like large amounts of climate data, into something that is much smaller. Yeah, so I'm a PhD student in Oxford and supervised by Miha and Juan, who I think also are both listening now. So to the two, yes, you will also see some new results. So in terms of compression, data compression, it's always a trade-off. So we could either end up with preserving a lot of information, but then we have something really big. And if we want to compress that down, we either end up in one edge of the trade-off where yes, you have to store a lot of data. You need to buy a big data archive, or you end up in the dilemma that you lose a lot of precision, which you probably don't want to do. Or it's a question of speed, right? So you could, for example, just save your forecast model setup, but then you would need to rerun the whole thing in order to regain the same information. So that's obviously not desirable. And so the question is really, is there something somewhere in between where you have a small amount of data that preserves the precision that you need, and as well that you can like easy read and write this data. So the data that I've been looking at is from the Copernicus Atmospheric Monitoring Service. So that's the CAMS data that was already talked about in the last talk. So we have about 50 air quality variables, so including like nitrogen dioxide, ozone, sulfate, but also aerosols. And at the moment, there is about 9 terabytes produced every week. So that means if you calculate that down, it's basically producing data quicker than, for me, on my internet connection, I could ever download. And the data is also quite, it has a lot of different features because there's a lot of different physical as well as chemical processes going on. So for example, here just showing nitrous dioxide in the stratosphere, and you can see the impact of the sun, as well as you can see some turbulence and winds blowing everything around. Whereas then once you go to the surface and basically in the same data set, just like further down, you can even see ship tracks and then the impact, for example, of industry. And so what I want to tell you in the next 10 minutes are some perspectives for how to compress this data. So currently we're and I will talk a little bit about the details of what that means. We're currently at a compression factor of 1.3, meaning that you could store the same data 1.3 times. So there are some solutions that I propose. One is the short-term solution, which I will go into detail, but this is what I call log quantization or log packing. Then there's a medium-term solution, the technique that I call round, combined with lossless compression. And then there's a long-term solution, which is the ZFP algorithm. And you can see the compression factors and how much that actually could benefit it. We will talk a little bit about information entropy, and as I don't know how many of you know or have an intuitive understanding of information entropy, I just provide you a little very quick example to give everyone an idea. So definition of information entropy is basically just you sum up P log P, whereas P is a chance. And so the sum over all these chances should be 1. So if you look at this at a die with 8 sides, and let's roll this die, then the outcome of either 1 or 8 is always 1/8. So if you calculate the information entropy of that, this 3-bit, because the outcome is either, and then you can basically just encode this into into bits 0, 0, 0, 0, 1, and then you basically have all the 8 outcomes, and because they're all evenly likely, the entropy is maximized. So we have actually 3-bit. Now imagine you have actually this die loaded. So that means that some outcomes are always more likely than others. And I've just like written down some chances here. If you calculate the entropy for that, you actually end up with something that is only slightly above 2. And the reason is basically because if you roll the die, you basically already know that the first bit will always be 1, because it's super unlikely that the rest happens. And so from an information point of view, you basically don't even have to store the first bit, and you would be well off just storing the remaining 2. That's kind of the idea behind it. And so what is currently done in all these data sets is that a method that is called 24-bit linear quantization. So you basically just take all your values, you look at the minimum of the values, you look at the maximum, and you just divide all the chunks in between into 2 to the power of 24. So that's something on the order of a couple of million steps in between, and then you basically just reassign them, and you basically just number the values. That basically avoids that you encode anything that is larger than any of the numbers that occur in your data set, and that you encode anything that is smaller than that. Sounds like a very intuitive and reasonable idea. The problem is, though, that if you look at how often any of these chunks actually appear, so these ones here, how often any of these appear, you actually see that well, there's a lot of bit patterns happening around or occurring around the minimum, but there's basically nothing happening for most of these for these quants in the quantization. So if you calculate the entropy of that, although technically you could have 24, you only end up with 16. So technically you're only using 0.4% of the bit patterns, which is like a very, very big waste. If you do the same idea, but instead of spreading these quants evenly, but if you spread them in a logarithmic fashion, so here, for example, let's say we don't use 24-bit, we use 16-bit, and you do the same again, and this is again nitrogen dioxide here, you suddenly see, ooh, there is some kind of pattern occurring, and we kind of make use of more or less all of the bit patterns. So if you now calculate the entropy of that, you actually get something much, much closer to the maximum entropy, which in this case here in this plot would be 16, and we actually end up with 15. So technically we are only wasting 1 bit. You cannot just do this for one variable, but you can actually do that for all of them. So the variable that we've looked at before is nitrogen dioxide. That's the orange thing here up in the middle, and the logarithmic entropy is on the left, whereas the linear entropy is on the right. And you can see that actually for the whole data set, most of these are like, no, almost all of the variables. There's a few exceptions up here where it basically doesn't really matter whether you encode them linearly or logarithmically. Most of them are actually logarithmically distributed. And so it doesn't really make sense to encode them in a linear way. And then already one thing to bear in mind is that, I mean, logarithmic distribution sounds really nice, and sounds really nice to chuck it in these parts, but actually the floating point numbers that we already start from, they are already approximately logarithmically spaced. And so this is something to keep in mind, because this will be the next method that we'll look at. So we can basically do this now for all of the variables, and you can see the long list here on the left, where you have all these different aerosols, and then there's some alkanes and alcohols along there. There's like the sulfates, blah, blah, blah. And you can look at things like the mean error, absolute error, decimal error. And then I have basically put the linear quantization in black and blue, and the log quantization in red and orange. And you can see that actually you could very safely replace the 24-bit linear packing or linear quantization that is currently used by 16-bit. It will be smaller, right? Because you only store 16-bit per value, and you have very much comparable errors. And some of these errors, especially like decimal errors, are actually much better bound, whereas like the maximum errors of these linear packing actually can be quite large. So that sounds like a good technique. However, as I said, floating point numbers are already logarithmically distributed. And so the underlying issue with floating point numbers is that if you have a floating point number, and here I'm just giving like a little example, you have a sign bit here in the front, you have the exponent bits, you have the significant bits. The point is that many of these significant bits actually do not contain real information. However, they appear to be more random. And so if you want to compress that, compressing noise is very, very difficult, because there's no underlying pattern to it. And so basically, these bits here basically has almost full entropy, and so you actually have to actively chunk them away. You somehow have to delete them, and you can do this, for example, by rounding. So if you round this number here, then okay, you have a little carry bit here that goes over, but otherwise all of them are 0. You introduce a little error, but basically this is much easier to compress, because if everything is 0, then it's quite easy to remember. And I just show this here. So let's say you have some kind of, it's often called then in data compression a 1D bit stream, so just like a long chain of floating point numbers. And if these are your floating point numbers, what you can do is that you basically just somehow round away the non-significant bits here at the end. You have some rounding happening here, and then because we're looking at climate data, and we always have some kind of correlation in space and time. And if we unfold this into like a 1D bit stream, then we could think of this either like going along the longitudes or latitudes first, or in the vertical first, or in time, whatever. But you will have some kind of correlation. So always knowing what your value is, your next grid point will be very, very close to that. And so you can basically, the idea of this, and this is what I call the round plus lossless compression, is you round this is correlated. So actually what if you want to compress that, you only have to remember the first bit here, then the bit that is different for every value, and then you have to remember the last bit. And so going from 160 to 60 bit down, you see that there's already big compression happening. To generalize this idea of a 1D bit stream, this is basically what's exploited by the ZFP compression. So instead of just looking at a single one-dimensional array, you can do this also for like 2 to up to 4D arrays. And here's an idea of like a 3D array, where you basically just chunk up everything into small blocks. And then you basically do the same technique in these small blocks. But then the idea is that the values inside such a block are very well correlated and therefore very compressible. And so this is just an example here from the ZFP website, where this chunking into blocks, once you have really high compression ratios, becomes evident here. However, if you have like medium compression ratios, then you see actually you can't really detect these underlying blocks. So summarizing all of that, this is now the absolute error and the decimal error for all of the variables in the CAMS dataset. And the linear quantization, as before, only has a compression factor of about 1.3. So the compression will always end up down here, with errors widely spread depending on which variable you actually look at. And especially the decimal error can have really, really big values in this linear compression. If we would go to logarithmic quantization, because we're only using 16-bit now, for example, we actually end up with a compression factor of 2, and the decimal, especially the decimal, we would gain that the decimal error is much better bound than it was before. If we want to go to even higher compression factors, so like round plus lossless here, basically on average reaches a compression factor around factor of 10, something between, let's say, 10 to 15, depending on the variable. Some variables are very, very well compressible. Some others are not that much. Yes, we would need to take into account that the absolute error would be slightly larger, but it's still well bound. And having something on the order of like, I don't know, a few % error, I think that is, I mean, I would need to talk to the presenter of the last presentation what actually the errors are in the observations, but we have this is still well bound. And then especially the decimal error, we only get like a decimal error of, let's say, again, like a 1% or so. There are a few outliers here, but it's definitely way better than where we currently are. So basically going back to the timeline, as I said before, so uncompressed, this is what we currently are, and this is basically where we can get with these different techniques. To make this all a bit more visual and to aid people to understand what's actually happening here, basically just plotted this on a globe with the compression factor, so uncompressed on the left, and then we have another slice here of then increasing compression factors for this round plus lossless technique. And you can easily end up, you can see here, once you have the compression ratio too high, it looks a bit like a comic. So that's definitely not what we want, but having something here on the order of factor of 10 or so, this is definitely feasible. And I would believe that everyone's very happy to work with this data. For ZFP, because of making use of the 3-dimensional structure of the data, you could probably even end up here, let's say this slice here with like 40 times compression for this. In this example, this is ozone. If you would go too high with the compression, you can see this. You can see here again this block structure appearing, and that's definitely not what we want. But like compression factors between 20 and 30 are definitely possible. So just to summarize that, currently, let's say we have 1 gigabyte of this data set, and if it was uncompressed, here 1 gigabyte. What we currently are, we're compressing it down to like 750 megabyte. Short-term solution is the log packing or the log quantization, which reduces this data set down to half of that. And then if we actually like medium turn is this round plus lossless, where we end up here with like something on the order of 70 megabyte. And if we actually would exploit the ZFP algorithm, then we basically can compress the same data set down to 30 megabyte. So if you find that interesting, just you can check out the repository. I will definitely in the next month update that so that all of this information is nicely viewable in the README. You can always contact me. You can find me on GitHub as well as on Twitter. And I'm happy to take any questions. Thank you.
Thank you, Milan. This is, I think, not only for CAMS data of high importance, but in the era of big data, I think very, very important work you do.